has already briefed their board of directors plan on the award fee.
Well, good morning. Thanks to everybody for coming. I find it kind of ironic that the person who's talking about this subject probably has among the least amount of experience of people here, but we'll try it anyway. We're going to talk today about the mathematics of multiplicity theory, and specifically what I'm going to talk about today is how you go from having special nuclear material in a sample to generation of neutrons, and then moments of the neutrons, or singles, doubles, and triples counting rates, and how you can go from those rates back to what the mass of the special nuclear material is in the sample. That's all I'm going to cover today. There's actually a second part to multiplicity theory, and that is how do you detect those neutrons with traditional multiplicity counters, namely counters that have helium-3 embedded in some sort of moderator. How do you go from the pulses you get from that counter to back to singles, doubles, and triples? That'll leave for a different lecture, simply because there's too much information to cover in today. So we're going to talk, again, like I said, mathematics and multiplicity theory. Basically what we're going to do is go over what Bunnell developed back in 1985, how we developed going from basic principles all the way out to the standard point model that we use today. So in the talk, we're going to discuss the origins of the multiplicity equations, including how neutrons are generated in sample and how that goes into and becomes the standard point model. And also how, in this theory, you can try to incorporate additional effects such as alpha and neutron energy into the theory in a fundamental way. We're then going to look at, just quickly, what the effects of the assumptions are on the standard point model, how that affects the assay results, and then what recent developments that many people in this group have done to try to advance multiplicity theory, to go beyond what's the standard point model into other developments. Okay? So let me just review quickly what neutron multiplicity counting is. In essence, what we're trying to do is use the multiplicity distribution of the neutrons that are emitted from the sample. In other words, how many times you get a single neutron, how many times you get a double two-neutron event, how many times you get a three-neutron event, etc. Emitted from a sample containing special nuclear material as a means for determining the mass of the special nuclear material that's in the sample. In other words, use it as an assay technique. Okay? One of the critical features of neutron multiplicity counting is that it is essential that the model that you're using to interpret the measured probability of the sample emitting n neutrons, which I'm going to call E of n, accurately describes the physics that is ongoing in the sample. In other words, depending on how well your model is in modeling all the physics that's undergoing, the induced fissions that are happening, how much spontaneous fission is occurring, how many alpha n reactions are occurring, depending on how well the theoretical model is, will affect how well you can assay your sample, how well you can determine the mass of special nuclear material in your sample. Now, one thing to keep in mind is that this probability is discrete. In other words, you only have values, probability values, for integer numbers of neutrons. 1 neutron event, 2 neutrons coming out, 3 neutrons, etc. It's not continuous. You can interpret it continuously, but because this is a discrete probability, it has certain mathematical features that you have to keep in mind. And it's a little bit more challenging for those of us coming from a physics background to handle in a certain way, in many ways. Before I get into the actual theory, before I get into the actual derivation of the point model, there's a mathematical technique that needs to be understood, or at least you have to be exposed to, and that's known as the probability generating function. What is it? If I'm going to give you a bottom line definition, it's a mathematical trick. What it is, that by formal definition, is a formal power series whose coefficients encode information about the probability that a discrete random variable is exactly equal to a particular non-negative integer. What does that mean? What does this mean, in essence? Let me show you the definition. So this is the probability generating function. It's just equal to the summation of the probability for the realization of the integer random value times some dummy variable to the nth power. Basically, it's just going to be a string of powers of u where the coefficient tells you the probability that some variable is equal to n. In other words, if I have 1 neutron event, this will tell me what the probability that I have a 1 neutron event. If I have a 2 neutron event, this is the probability that I have a 2 neutron event, etc. It's just a simple way to keep track of what these probabilities are, and in a functional form that has certain probabilities that are desirable in doing these derivations. Okay, that's all it is. It's just a mathematical trick. It's a mathematical accounting technique. But there's some really nice features when you have a probability generating function. Let me give you 2 examples just to make sure we understand this concept. Part of the problem with probability generating functions is they're non-intuitive. You can't really look at them and get a good feeling from them. If I have some variable which is just equal to a constant, I can write a probability generating function which is just simply u to the c. What does this tell you? This just tells you that 100% of the time, because this coefficient is 1, you get n equal to c. Really simple. Let me give you a second one. Those of you not familiar, a binomial random variable, think of it as a coin toss. What's the probability you get heads in a single coin toss? What's the probability you get tails? Okay? So if I have t trials, and I have a probability of s success, and a coin toss, this is about 50%. I'll say about because there's actually slight different weight on either side of the coin, but we won't talk about that. S success after each trial. So I can write a probability generating function where this thing is the probability for success times u to the n. If you do some mathematics on this, what this comes down to is a simple equation that basically says, for example, if I have just one coin toss, I'll have a probability of s of getting n equals 1, we'll call it heads. So I have an s probability of getting heads and a 1 minus s probability of getting tails. If this was 50%, this would be 50% getting heads, and 1 minus s is 50% for getting tails. Because each coin toss is independent, the result of the next coin toss does not depend on the previous coin toss. It's just this multiplied by itself n times, or this thing to the n power. Okay? Are there any questions so far on probability generating functions on like this? This will actually show up a couple times in the derivation. Why are we even introducing probability generating functions? Because of its properties. The properties help you manipulate what you need to work in the mathematics in order to come up with something useful in the end, something that you can work with as an experimentalist and measure. The first relevant property is the fact that if I take the derivative of the probability generating function as a function of the dummy variable and set the dummy variable equal to 1, what I get out is this. This you can just easily do by doing derivatives. But what this is the ith factorial moment of the probability distribution. This is what we end up measuring in multiplicity counting in this group, is singles, doubles, triples. Those are just simply related to the factorial moment of the probability distributions. So the way to get at those using probability generating functions is just taking the derivative and setting u equal to 1. Okay? It's something easy, relatively easy you can do, compared to if you're working with probability distributions themselves, or probability density functions. That's another way of phrasing it. The second property is that if I have two independent random integers, we'll call them n1 and n2, with their respective probability generating functions, f1 and f2, then if I have these two equaling some sum, then I could simply multiply the probability generating functions. It looks trivial, but if I wasn't working with probability generating functions, if I was working with probabilities or probability density functions, this would not be a simple multiplication, this would be a convolution. And for those of you not familiar, convolution is a bit more extensive than a simple multiplication. It again simplifies how I deal with the math, conceptually. The third property is, this probably took me quite a while to figure out. The formal definition basically says if this probability generating function is formed with conditional probabilities, which I'll call R for the value to be n, based on the condition C, then, and if the probability for the condition C occurring is P of C, then the probability generating function for n is just the probability that the condition occurs times the probability generating function for the value to be n based on that condition. Okay? This actually appears quite often in the derivation as well. So why don't I go ahead and just show you how that property comes about. You can actually prove it to yourself relatively quickly. Again, I'll just define a probability generating function. I'll define my probability in terms of a sum of conditions of the conditional probability times the probability that that condition will occur. Okay? What do I mean by this? What practically can we think of as this? Well, the conditional probability is just the for example, this could be just the probability of n neutrons being produced from induced fission. Okay? If induced fission exists, then this is the probability that n neutrons will be produced. This, the PC then, in that case, is just the probability of induced fission occurring in the sample. So once you have an induced fission, this is the probability that n neutrons would be emitted. Okay? So if I substitute that into this formula, we get this equation right here, which if I do some swapping around, and I define this probability generating function is just equal to the conditional probability times u of n, then I get this. Okay. This will appear several times in the derivation, that's why I bring it up. Okay, and it's a very useful technique. It also shows you how you can build probability generating functions basically on top of other probability generating functions. It gives you some nice properties when working with the mathematics. Okay? Let's get into the actual derivation, now that I've shown you some of the mathematical techniques that are needed. This is based, all of this comes from Bunnell's paper back in 1985. Okay? There is a separate derivation that was done by Haag and Cifarelli. They both end up with the same conclusions. Haag and Cifarelli tends to be a little bit more brute force. It tends to come from more of an intuitive point of view. The reason I want to show you this is show you how it kind of all connects together in one more complete story. And you can do it, for me, a little bit more logically, or kind of evidently. So let's first of all look at neutron generation in the sample. Let's assume the event rate from the sample is just coming from two sources. One is the spontaneous fission rate. So we have some nuclei in there that are spontaneously fission. And we have some impurities in the sample that are producing alpha N reactions. Okay? And we're going to just set a total event rate is equal to the sum of these two. All right? This makes kind of an implicit assumption that the neutrons from both the sources can be treated equally. In other words, I don't know, when I have a neutron, it can be either from alpha N or spontaneous fission. I really can't tell the difference. This is not exactly true, but we'll just make this assumption to help with the derivation. I'm going to introduce another quantity, which is the probability of emitting new neutrons from a source event in the sample. We'll call it Q. And all this is going to be is just the relative amount of spontaneous fission reactions that are occurring in the sample times the probability of emitting new neutrons from spontaneous fission plus the relative number of alpha N reactions that are occurring in the sample times a delta function, because only one neutron comes out of the alpha N reaction. Okay? I'm going to do some more definitions on the next slide. So let's start working with multiplicity. How do you start developing the probability generating function? Okay, so the probability generating function for the number of neutrons generated from a source event could be either spontaneous fission, it could be alpha N. We're going to call it F, and that's just going to be based on the definition here. That's just a simple definition. It's just a simple definition of probability generating function. The probability times u to the n. Okay. Anytime you see F, think of it as a source term, in essence, in this derivation. We're going to do the same thing for induced fissions. We're going to call it F sub I. And we're going to do the same thing again with Q being the probability of emitting N neutrons from induced fission. Notice I don't have any type of energy term on here. I don't have any conditional probabilities. We're assuming this to be energy independent. It is just what it is for the sample. We don't consider neutron energy at all. Now, since I've mentioned induced fission, let's discuss how we're going to treat it. We're going to let P be the probability that a neutron induces fission in the sample, which of course implies that 1 minus P is the probability that a neutron leaves the system, somehow. Most likely it leaves the surface. It could include neutrons that leave the system via reactions in the sample itself. So if you have neutron poisons, or if you have something that the neutron will react with and it leaves the system, that falls under this number. Okay. In reality, though, this probability really depends on the position of the neutron in the sample, where it starts, and where it's going to. Okay? A neutron, so really P should be a function of the position and the momentum. A neutron that's born in the center of a large sample goes through a lot more material and could probably induce fission, have a higher probability of inducing fission than a neutron that occurs on the outside of the sample, that's born on the outside of the sample. Or a neutron, if two neutrons are born in the same place, but one goes in a direction that encounters more material than a second neutron, it depends on the direction or the momentum of the neutron, where it's heading. And it also then depends on the energy of the neutron, because the induced fission probability is energy dependent. Depending on the incoming neutron, induced fission will produce different number of neutrons when it fissions, and it also has a different probability of inducing fission. But in order to simplify this, because this will get really messy really fast, and it's going to be dependent on what the sample looks like, what the composition of the sample looks like, we're just going to simplify the calculation and assume T is a constant throughout the whole sample. This brings in the concept of a point model, and it also brings in the concept of being energy independent. It doesn't matter what the neutron energy is. This is the number we're going to use. Okay? So let's consider one source neutron. If we have one initial neutron in the sample, and we're going to call L of n the probability that n neutrons leave the sample as a result of that neutron, then again, we're just going to use the standard definition of probability generating functions and call it h of 1 because we're dealing with one source neutron. It's just equal to this. Now, if we have s initial neutrons, and we treat them independently, like we treated a coin toss, like a coin toss is independent each time we do it, then the h of s, the probability generating function for the neutrons to leave the system for s neutron based on s initial neutrons, is just going to be the probability generating function for one initial neutron to the power s, just s number of h factors of this probability generating function. Okay? So this is basically just telling you how, when you start with, in this case, one neutron, how many neutrons come out? What happens in the sample with that one neutron? So whenever you think of h, I kind of think of it as a propagation term, as a way of neutrons, when they start, how do they leave the system? How many leave the system? What happens to that neutron? Or what happens because of that neutron? Think of this kind of a propagation term. Okay? So let's look at neutrons leaving the system. So in the case of a system with finite probability of neutron-inducing fission, in other words, you have, for example, plutonium-239, you have some isotope in there that induces fission. The probability generating function for the number of neutrons of all generations that leave the system due to one source neutron is, here you go. This first term basically just says it didn't induce fission, it left the system. So we just have a 1 here. One neutron left the system. So there's a probability for that. Plus there's a probability that it induced fission. This is where it gets a little tricky. So P is the probability of induced fission. Q of n tells you how many neutrons were induced by that fission. And because we're trying to determine how many left the system, we need to, again, propagate them out of the system. However many neutrons were produced in the induced fission, we have to propagate out. There's a little bit of math you can do to show that this is true, but you can come up and show that this is just the probability generating function for these neutrons to leave the system. Okay?
Wait a minute, well, you've got two subscripts, I and n, you're summing over n. What happens to
I is just the induced fission. Probability of inducing fission.
Oh,
that's just get identified.
It's not a
right. Now, one thing to keep in mind, those of you who are familiar with Bunnell, I'm kind of changing subscripts and scripts around a little bit to make a little bit more consistent, make it a little more sense, and try to match things with what comes out of, for example, the neutron application guide or anything else on the standard terminology we use. I'm trying to match it all. So this is the first attempt. So this just indicates that this is the probability for inducing fission, the probability of n neutrons coming out of induced fission. This P is the probability for inducing fission, and this is just propagating the neutrons that come from induced fission out and to see if it makes it out to the surface of the sample, makes it out of the system. Okay? We can basically manipulate things. We can take the P out because it doesn't depend on n. We've shown before that if you have this case, this is really just n, h1 to the power n, one source neutron, n times n factor, to the n factor, I should say. So what I'm going to call this ends up just being the probability generating function for induced fission, how many neutrons are produced, with this. Basically think of it as source term, and I'm propagating those neutrons. I'm producing neutrons from induced fission, and I'm propagating them out. Okay? So this is one of the essential pieces we need, how to get the neutrons from the source outside the system. We're going to, simplicity, we're going to rename H1 to just H, with it being understood it's for one neutron, one initial neutron. Okay? So with that piece and with the source term that we created, the source probability generating function we created before, we can now introduce a new probability generating function, we'll call it capital H, for the number of neutrons leaving the system as a result of a general event. Okay? The first piece we did was how many neutrons come out of a general event. The second piece we did was how many neutrons, when we start with one, will come out of the sample. Now we're going to combine the two. Okay? We're going to call E of n, as I mentioned before, the probability of n neutrons leaving the system as a result of a single source event. Okay? This is basically what I called before the probability generating function F, with including the propagation probability generating function. Okay? So let's look at it this way. It's the probability for neutrons to be produced, and this is the probability generating function for those with one neutron to produce more neutrons, or how many neutrons come out because of the neutrons produced here of the system. If I just take and directly substitute what this is defined as, we come down here and we see that we have a term due to alpha n neutrons, basically the relative number of alpha n reactions, since they just propagating them out, because it's just a single neutron, because we have this delta function here, we only have one neutron coming out. I can pull this out and just call it this. And then we have the fraction due to spontaneous fission reactions, how many neutrons are being produced, and how many actually come out of the system. Okay? Okay. Just keep asking questions when you have it. This is a lot of dense stuff that I'm trying to cover. All right, so like I said before, we measure the moments of this distribution. So let's go ahead and start deriving the moments of this probability generating function for En. So the first factorial moment is just simply the derivative of h with respect to u, setting u equal to 1. I'm just taking this derivative and taking it to the two components here. Let me first work on this, taking the derivative of dh du. Okay? So, first derivative of h with respect to u. Here's the definition again. I'm just applying the derivative to each component of the definition. This was 1 minus p times u, so this is just the derivative of u, setting u equal to 1. And again, we have the derivative of the induced fission probability generating function with respect to u. One trick to keep in mind is that because we're taking the derivative of a function, we could do this. Take the derivative of the function with respect to h of u, and then take the derivative of h of u with respect to u. That's just calculus. Yeah. So now that we have dh du on both sides, we do an algebraic trick. We bring this over here so that we have all terms related to dh du on one side, and we solve for it right here. Okay, so now what we're saying is the first derivative of h, or another way of possibly thinking of it is the first factorial moment of the small h is equal to 1 minus p over 1 minus p df, the induced fission probability generating function dh, evaluated at u equal to 1. Okay? Now, what does that mean for us? One thing to keep in mind is, since h of u is a probability generating function, what does that mean? If I just set u equal to 1, h equals to 1. Why? Let's back up a second. This is a series of probabilities. If I sum this out, this would be just L of 0 plus L of 1 plus L of 2, L of 0, U of 0 plus L of 1, U of 1, etc. If I set U to 1, then all this is the summation of the probabilities. And if it's properly normalized, this better be 1. In fact, it has to be 1 when U is equal to 1. Because all I'm doing is summing all the possible probabilities that make this up, and that better equal to 1. It's just a normalization of the probability. So, again, probability generating function, when you set the dummy variable equal to 1, it's just equal to 1. That's just indicating that you've normalized your probabilities that make up the probability generating function. So what I could do is do a substitution of variables and say, instead of saying the h of u, I'm just going to call this h, and instead of saying u equal to 1, I'm going to say h equal to 1. So basically what this is the first factorial moment of the number of neutrons that are produced due to induced fission. Well, I'm just going to call that nu I1. Okay? And in fact, this is going to be a known quantity depending on the isotope you have that's inducing fission. This is something that's been measured and quantified and is in the data sheets for various nuclei that induce fission. Okay? So this is in essence a known parameter. I won't say it's constant because it depends on energy, but it's a known parameter if you know what the isotope in your item is. Okay? So this means that the first derivative of h with respect to u is this, which has been called in both Hagen-Cifarelli and as well as members of our group as the leakage multiplication. What does this tell you? It tells you when you have one initial neutron, on average, you have m neutrons coming out That's leakage multiplication. If I have one initial neutron in the sample, m, on average, the mean, m neutrons come out. In other words, one neutron multiplies into m neutrons, on average, the mean. Any critiques or questions on this?
Yeah, I do. I have a question on the first equation. When you did yes, when you did that substitution, again, I would apply the chain rule. So if you have df dh of u, you just do the chain rule, and you have df dh times dh du.
I've already done that. df dh, dh du, I already did that. That was done before. This is the df dh.
Right, but it's, I'm just simply, you apply the chain, I know you did it before, and that's why I'm confused. So what you want to establish then is that dh du is equal to 1, not h is equal to 1, but dh du is equal to 1.
Yes, except I'm evaluating at u equal to 1. I'm evaluating it at u equal to 1. So if I show that if u equals 1, h equals 1, it's the same thing. Because I'm doing it at this particular point, not the whole probability generating function in general. That's the trick that's used. Now, this is straight out of Bunnell. I've looked at it, I agree with it, but if someone can come up with an argument saying that's wrong, we should talk about it.
I'd just make a point of clarification on your use of the term leakage multiplication. Later on, that could get you into trouble, because later on, in going from this point to where we go to our point model equations, we assume that nu I1 is a certain quantity, and that quantity is a fission moment as opposed to the way it's being interpreted here, which is where P includes both. Essentially, you're looking at P as the probability of a neutron leaving the system.
No. P is the probability
I'm
of...
sorry, 1 minus P is the probability of the... In other words, capture is not... capture is kind of implicit in here. It is not explicit. And leakage multiplication usually includes capture.
Right.
So if you interpret nu I1, if you interpret this in the absence of capture, it's really a fission multiplication and not a leakage multiplication. If you assume your probability in the absence of capture, if there is no capture going on, M is really... Later on,
yes.
The equations look more like a fission multiplication than a leakage multiplication. So just
right, but
sort of keep that in mind.
Remember what I said about this. This just tells you that a neutron left the system.
Right.
It does not tell you how. This could be neutrons escaping the system that you can detect. This could be neutrons that you lose in a reaction. I don't distinguish between the two in this probability.
Yeah.
The only thing I've positively defined is the probability that I've induced fission.
My point is that later on the equations look different because of the interpretation of the nu. But keep going. Keep going.
Well, I think you'll see. Well, okay, let's just go on. So with this, we now go to here, which is basically what we wanted. First moment of the total probability generating function. We have just multiplication times the relative number of alpha n reactions, and multiplication times the relative number of spontaneous fissions times this quantity. It's basically the exact same math that was done in the previous slide is done for spontaneous fission, and we're going to come up with this for the moment. So it's just S alpha plus SSP times nu S1, where nu S1 is the first factorial moment of the spontaneous fission neutron distribution. If you want to do the second factorial moment, it's very similar. There's one new trick that comes up. It's just the derivative parts, derivation, the product rule for derivative. In other words, you have to take the derivative of the first times the original second plus the original first times the derivative of the second. That's how you get this. That's your only the other real trick that you have to do. Otherwise, it's very similar. So that you end up with the second derivative of the small h being this, right here, where I've done algebraic substitution for P over 1 minus P di1 as being this. Okay? I won't go through all the math, it's just mostly the same thing I did in the first factorial moment. If you don't understand, I can help you with it later on. Okay? But you do the same thing with the second factorial moment, you end up with that equal to something that's starting to look very familiar if you're familiar with the point model. okay? Where again, I've introduced VI2 as the second factorial moment of induced fission, and VS2 as the second factorial moment of spontaneous fission.
Where do you, where are those defined in the equations? That is, where I'm getting lost is that all of a sudden those terms appear, but they did not appear earlier.
That's fine. The VI2 comes from when you take the second derivative of Fi with respect to H and evaluate it at U equal to 1, or H equal to 1, excuse me.
So you're defining nu I2 as that quantity, it's definition.
Yeah. Because this is the number of neutrons that come from induced fission. This is the second moment of that distribution. This is the second moment of the number of neutrons that come from induced fission. Back up. Second. I want to show you something.
I think I see what you're doing.
Here. If I want to get the moment of this, I take df du, evaluated at u equal to 1.
Right.
U is a dummy place. I don't care if I call this u, I don't care if I call this h. So long as I said this equal to 1, and this is raised to some power, df, d dummy variable, set equal to 1, is the moment, factorial moment of this distribution. Okay. That's why I'm kind of getting back to what you're saying. Because I'm doing this is by definition this. There is no other way of stating it. This is just being defined as what I could tell from Norbert. Now, that, I don't know. I mean, I've seen definitions for both the normal multiplication and leakage multiplication. From what I can tell, this is the definition of leakage multiplication. We can discuss that.
Sometimes you see it with another term in the denominator.
Yes. Okay.
Yeah.
But this is why we're doing...
where I was going when we started interpreting what that nu really means in terms of the physics, in terms of what we measure later on. It can get a little confusing when you get captured in the picture.
Yeah. No, I agree with that.
Yeah.
That's why I was trying to point out that this could include capture. One thing also to keep in mind is the reason we're going through this in terms of what we want to do internally is there's a lot of different works on this that use different notation, and different concepts come in, and they're trying, and different works that try to combine different things, and it's not been very clear. I'm trying to make a very clear, concise document will eventually come out of this that has everything you need, kind of, and not necessarily in a straightforward manner, but all consistent, and with as much explanation as needed for the reader. Okay. So, your question again, VI2 is coming from this, right here, or this, I should say, and then the VS2, or new, I'm sorry, these are new S2, is coming from this, right here. Again, it's just the moment of the probability of inducing neutrons from spontaneous fission. The second moment of spontaneous fission, neutrons coming from spontaneous fission, excuse me. Right. And for those of you not convinced of the trick I showed you earlier, here it is. You can just, by definition, just go along, do the algebra, and find out that this quantity is really equal to this quantity. They're equivalent. The reason we do this is we don't want p's in our system and m's. You kind of want to just have one variable to describe this. You don't want two, because then it looks like you have to have more measurements than you actually do. Third factorial moment gets ugly if you're not used to it. It's actually just long. No real new concepts here. Again, product rule when you do derivatives. You actually start getting combination of terms. The derivative of the second part here and the derivative of the first part here actually end up being the same exact term, so you can combine these two. That's where the 3 comes from. This is more for the benefit of those who've actually looked at the equations and wondered, where the heck did I get a 3 from? It's coming just from the actual following of the math. Okay? So, going to the next slide. Again, VI3 is just coming about because of this. Third derivative of the probability generating function for induced fission as a function of H. So that's where we introduce the VI3, the new I3, excuse me. I'm going to use the actual 3 for this. Okay, so that you end up for the third factorial moment with this equation. Okay. And again, we've introduced, back up one slide. I won't show it, but again, this becomes introduced because you're taking the third derivative of the probability generating function for spontaneous fission. Okay. You use the exact same process to derive any other higher order moments of the distribution you want. Now, there's some question in recent developments where people want to look at the actual probability distribution rather than the moments themselves. a bit of a misnomer because they're equivalent. There's just a little conversion factor between the two. Okay. Now, so there's a way to get, the basic point of this, don't spend too much time on it, then you can get back to the original probability distribution through this methodology. It's very similar to taking moments, except you set u equal to 0. So, let's go on. So now what I've shown you is the moments of the probability distribution of neutrons being emitted from the sample. We got to convert those into rates, because we measure in the laboratory neutron rates. So, we can calculate these rates at which the number of neutrons escape the sample per unit time in groups of n. So there's the rate multiplied by the total event, the rate of these groupings of n. It's just the total event rate times the moment of the probability distribution function for that particular neutron, divided by n factorial. The n factorial is introduced to correct for multiple counting of the same event. In other words, if I have, for example, 3 neutrons, we'll call them neutron 1, 2, and 3. If they come in the order 1, 2, and 3, it's technically different than if they came in the order 2, 3, 1, or if they came in the order 3, 1, 2. For our purposes, they all look the same. It's the same 3 neutrons, and that's all we care about is that we got 3 neutrons. So we have to correct for this multiple counting with this factor of n factorial. We can use these rates then to determine the unknown quantities of the sample, namely the number of spontaneous fissions occurring in the sample, number of alpha n reactions occurring in the sample, and how much multiplication is in the sample. Okay. The values of the spontaneous fission and induced fission moments, nu Sn and nu In, respectively, is dependent on what you had in there, what the composition of the item being measured. Let me illustrate that with a simple example. Let's take a californium source. This behaves via spontaneous fission. Let's assume that it contains no impurities, so we have a alpha n reaction rate equal to 0. And we have no isotopes which undergo neutron-induced fission. That means the probability for inducing fission equals 0. This implies that the multiplication equals 1, just by the definition of multiplication. I'll just call it multiplication from here on out. Then these rates just end up being shown here, this relationship to the moments with the number of spontaneous fission, the reaction rate in essence, showing up here. Okay. For californium-252, these numbers are well known, coming from Holden and Zucker in their most recent compilation. What I'm doing here is also introducing you to the concept of singles, doubles, and triples. Okay? Because this is what started me on this whole thing. I was looking for singles, doubles, and triples when I first read 1L, not there. So this hopefully will help people just beginning to understand what we mean by singles, doubles, and triples. That's for a californium source. That's not really what we're interested in. What we're interested in is plutonium, mostly. We can also do uranium, but let's just take a plutonium sample, a sample with special nuclear material. Okay? Plutonium samples generally contain several isotopes which decay via spontaneous fission, mostly the even isotopes. What we're going to do to account for this is to create an effective plutonium-240 mass, which corresponds to the mass of plutonium-240 that reproduces the doubles counting rate that is obtained from all the even mass plutonium isotopes in the sample. And here's how we're defining the effective mass, where we've come up with these coefficients by these ratios of taking the number of fissions per second per gram multiplied by the second spontaneous fission moment of, for example, 238 in this case, divided by 240, and this is equal to 2.52. Same thing with 242 to 240 to come up with these coefficients. Anybody see a mistake with these? I wasn't confident if it was this way, because the write-ups, and I didn't have a chance to actually calculate it myself, told me it was 238 to 240. I was like 90% sure of it, but if anybody sees a mistake, let me know. But I believe these are correct. So the spontaneous fission rate that we had originally called SSP is now going to be just equal to the effective plutonium-240 mass times the number of fissions per second per gram of plutonium-240, which some sources refer to as just M(S0), which other sources just refer to as F, which is just given as the spontaneous fission rate, number of fissions per second. Okay, depending on which one you look at in the derivation, these two or these three, all of them are used. So just to show they're all equivalent. So now let's go back to my moment and start looking at developing counting rates. Another thing that's done is, because the dominant decay mode of plutonium isotopes is via alpha decay, we're going to assume that the number of alpha N reactions which occur in the sample is related to the number of spontaneous fissions that occur in the sample. In other words, the source of the spontaneous fissions is the same source of the alphas that induce the alpha N reactions. They're related. They're not two independent quantities. So we're going to define this parameter alpha. It's defined as the ratio of neutrons from alpha N reactions to the number of neutrons from spontaneous fission. So alpha is just equal to the alpha N reaction rate times the fact that only one neutron comes out, divided by the spontaneous fission rate times the first factorial moment of the spontaneous fission distribution, or the mean number of neutrons that come out of spontaneous fission. So just doing the math, you end up with being able to substitute for the alpha N reaction rate, it's just being alpha times the number of fissions, spontaneous fissions per second times the number of neutrons being produced in those spontaneous fissions.
Peter, this is really my recollection of this is that it was mostly just a mathematical trick to make the equations come out a little more simply. I don't think anybody ever made the argument that you made up front there.
You have to if you're going to do this trick. I mean, you have to do it. Although, if I assume there's an independent alpha N neutron source, this is no longer true. Well, actually it is.
Yeah, I mean, it's a mathematical convenience.
Yeah.
It's a parameterization.
Yeah.
So,
But
yeah. Okay.
I'm kind of making this argument because it makes the most sense.
Okay.
I don't see any other alpha sources in these that I could conceive of in these samples. And so therefore
You got
can
americium in there.
Yeah,
Okay. So maybe I take out the statement.
Yeah, I would take it out because my recollection.
All you have to do is say, we're going to stipulate that there is a parameter that
It's just a
relates the number of
parameterization.
alpha N decays to fission decays, and you can stipulate that because the sample doesn't vary in time.
Okay. That's fine. I initially thought of it that way, and I thought maybe there's something more fundamental that we're saying. Or is there an assumption that's implicit there that we need to look at? That was my concern. If the experts in the audience say no, then I'll just take it out. That's fine. Okay, so we end up with single, doubles, and triples rates that are shown as thus. Okay, all I've done is done substitutions for the S alpha for the SSP to come up with these equations. Okay, notice I haven't put any detector effects introduced. This is just the singles, doubles, and triples as they're exiting the sample. Okay. Let's go ahead and introduce detector effects. We're just going to incorporate detector efficiency. Okay, so we're going to need a probability generating function for the number of neutrons detected when one neutron leaves the system. We'll call it B for detection. And it ends up being that binomial that I showed you earlier. Again, it's either you detect it or you don't, where you're calling epsilon the detection efficiency. Now, if I look at the moment of this probability generating function, you end up with just getting the efficiency out for the first moment, and all of subsequent other moments are zero. Okay? So now we're going to create a probability generating function. This is just to detect one neutron. Now we're going to create a probability generating function for the detected number of neutrons from an initial neutron. So you start off with one, you're now going to include any type of multiplication that occurs, and then detect it. So you start off with K. This just tells you that the neutron escaped, and therefore you just have to worry about how you detect it. This tells you that you had a probability for you reduced fission, how many neutrons came out of the fission, how many came out of the system, how many did you detect. Okay? It just builds up one on top of each other that way. The only reason I'm doing that is to show what the new probability generating function for the detection is. It's extremely similar to what you had before, except now you have different probability generating functions there. If I take a look, for example, at the first moment, what you end up with is this. We've already solved for that. That's nu I1. We've already solved for this. That's this quantity right here. And we now shown that this is the efficiency. If you work it through the math, you end up just with the efficiency times the multiplication. Okay? So basically all that does is add and introduce an efficiency, and if you do the mathematics, I won't show it now because it's very similar to what I just showed, you end up with the efficiency squared and efficiency cubed. Okay? So here right now is the point model multiplicity equations that everybody's familiar with. I've added an additional term here and here. These are detector effects. These are what's known as the double gauge fraction and the triple gauge fraction. I'll discuss those in the next lecture, because I don't have time right now. And I don't see a way that Bonnell introduces these at all. So, but for convenience, I've just introduced them so that everybody familiar with the standard point model can see them in their place. What does this do? Again, this converts singles, doubles, triples into the spontaneous fission rate of your sample, ratio of alpha n to spontaneous fission neutrons, and multiplication of the sample. In other words, a way to describe the sample. What were the assumptions that went into this? I kind of showed you as we went along where they were, but let's summarize them real quick. I've never introduced any type of concept of time. Induced fission neutrons are emitted simultaneously with the original spontaneous fission or alpha n reactions, known as the superfission concept. Basically, everything happens at once. The bad thing about this is it neglects any neutrons that are reflected back into the sample. It neglects any additional sources from those neutrons. This can be taken out through design with the counters, usually. We have a assumption of uniform detection efficiency and probability of fission over the sample volume, the point model. I showed you where that came in because we're assuming the probability of inducing fission from a neutron inside the sample is constant throughout the sample. This has severe problems when you have dense or thick materials because they have a variable probability of fission depending on where you are in the sample volume. Neutrons from alpha n reactions in the sample have the same energy spectrum as spontaneous fission neutrons. This is only strictly true for plutonium oxide. Any other impurities in there will produce different energy neutrons from alpha n reactions. Neutron capture without multiplication is negligible. This is not true if you have any type of poly, water, or poisons in your sample. Then you will have it. Whether it's significant or not, that's a different question. But you will have it, and how much effect you will see depends on how much of these items you have, these substances you have in your items. And at no point during this derivation have I looked at any type of correlations between neutron multiplicity and neutron energy, the energy of the neutrons that are emitted from the item. I've just assumed they're independent. So part of that was the whole point of if I have n initial neutrons, they behave independently. Mostly that's true, but there could be correlations. So what happens? Let me just show you some effects real quick. If you have a high multiplication plutonium sample, if I plot this leakage multiplication as a function of where I'm looking at the neutrons coming out of the sample, depending on at what point, you can see this leakage multiplication drops. In other words, it's a function of the geometry, as I've been mentioning. This, of course, starts to show trends and biases as a function of multiplication from data from, for example, the FD line neutron multiplicity counter. There's current work in this group to try to correct for that. Because those effects can be dependent on what you're using to detect it or what samples you have, a weighted point model has been created to try to correct for those multiplication effects, the variable multiplication that occurs. But this is really not fundamental. This is just sort of a ad hoc add-on that Merlin developed, and it works. I mean, it relies on MCMPX to calculate these correction factors, to take into account the properties of the item itself. And you can see from these measurements where before the standard point model, the bias was something like negative or 15% low. Now the average is very close to 1, much closer to 1 when you apply the weighted point model to the standard point model. Let me just skip that real quick. We also have issues with impure items. For items that were measured at the CAMS detector, if you increase alpha, you see increases in bias in different directions depending on the impurities that you have inside the item. These are metals here, these are oxides. So you can see the effect of that assumption of energy independence, possibly. There might be other effects due to alpha n reactions. The reason I think it's energy, if I look at Monte Carlo calculations using MCMPX, for a 2 kilogram plutonium metal cylinder in an ideal detector system. If I look at the point model, the assay to true ratio goes very low and shows a dependency on the alpha and neutron energy. If I apply the weighted point model, that gets corrected, but I still see this dependency. So there are some effects because of the alpha and neutron energies on the assay results. Now, how can one include energy dependence into Bonnell's formulation? What you would do is create a new probability generating function, which for basically the propagation of neutrons or for the detection of neutrons for each process involved. So X is just a notation of whether it's an alpha n reaction you're dealing with or spontaneous fission. You would have then separate probabilities for inducing fission based on the process, separate detection efficiencies based on the process. The way Bonnell presented this is only for the first generation, so you're only concerned about the energy difference from that initial neutron. Once you get beyond one generation, then you're propagating it and detecting it as if it was spontaneous fission in that. You're only dealing with a correction from the first generation only. Okay? And again, you can create a probability generating function for the number of neutrons detected in the system, including these effects. All right? Some work has been done in this way, combining both a weighted point model and energy dependent. This is something that I developed. I took a couple more assumptions in here. I'll just show it for reference. If you have more questions, you can ask. What's the summary? What we've done today is look at the essential assumptions of the point model, where they come from the derivation of Bonnell. And we've discussed these assumptions which cause biases for highly multiplying and highly impure items. I briefly touched about what new developed features we're trying to put in the point model based on MC&PX. And I am planning on having a future talk on dealing with the issues of when we measure reals and accidentals, how we convert those into singles, doubles, triples, because that's a whole new area of mathematics for multiplication, or multiplicity measurement efficiency. Thanks for your time. I'll go ahead and put those corrections in for alpha. Appreciate it. Are there any other questions, comments? This is eventually going to come in, hopefully be put into a review paper that will be distributed to the group for new members. So if anybody has any comments or things they want to see different, please let me know.
Could you distribute this?
The talk?
Yeah, because there's one spot I'd like to make a comment. And actually, it's not so much in what you put in the view graphs. We don't need to do it now.
Okay.
But what was said around the view graphs, and that's this whole issue of capture.
Okay,
Yeah.
sure. I appreciate it.
Because it does complicate things. In fact, the equations change somewhat if you put capture in there.
Okay.
I'd like to make a slight comment that there's one part that could be expanded is the issue of the definition of a probability generating function, what it is and why you do it.
Okay.
In that, what a probability generating function is essentially the Laplace transform of the binomial process. And the significance of it is that when the Laplace transform converts a convolution integral into a product, the probability generate a version of that is actually called the Z-transform, which is when you deal with discrete events. And when those discrete events actually have a value of 1, it becomes a probability generating function. But it's the same thing as a Laplace transform in that it converts two things into a transform space such that the transform variables or transform functions product is equal to the convolution. The significance of that is that the way that you add random variables is you convolve their probability densities, so that the probability generating function is a way of adding probability variables without doing the convolution integral. But it is based on the Laplace transform. A lot of people are more familiar with the Laplace transform.
Okay. I was, but I wasn't too sure of my audience, so I didn't want to bring in more mathematical terms than absolutely necessary. But I can try to introduce it. It might not be in the talk because I have a lot of information to cover, but I will definitely put it anyway.
In the paper, I think it ought to be there.
Okay. Could you just send me an email reminding me that? I'll put that in my folder. Thanks.
Nice work, Peter.
Okay.
Okay.
If anybody wants, I can distribute this